Hi folks, Mr. Long here with a second example, which is question number 6 in the making connections within the fundamental theorem. So we've got another situation here where we need to remember that the area under the rate curve from x equals a to x equals b, remember that f at x denotes rate. If f at x denotes rate, then the original function is f at b, or f at b minus f at a in this case. Okay, so this is area. An area of rate equals the change in y value on the original. Okay, that's really important. It's this relationship over and over and over again. And I encourage you, I implore you to go use that snow melt, snowfall context to help you think about this. So we've got not a lot of information over here, right? A lot of blanks there, but we have information that we can draw and get right off of here. This is a really good example because you get different pieces here. Okay, so sorry, I'm just drinking my coffee while I'm recording this. Okay, so here we go. What do I know? This is my rate curve, f at x, okay? And the rate tells me how fast it's either snowing or how fast the snow is melting. So this would be melt, because it's a negative rate. That would be melt because it's a rate. This means snow is falling. I want you to think, as soon as you see this rate graph, you need to think intuitively, just roughly, what would the original graph look like? Well, if we think about this, just roughly, again, we don't know what the y values are just looking at this graph. We only know if the snow is getting deeper or the snow is melting. So what would it look like? Well, if I've got the x values I've got on here are 2, 10, and 13. So 2, 10, and 13. Well, from 2 until 10, the rate is positive. That means snow is falling on the ground, so the graph is going up. I don't know the rate at which I kind of do, and we're going to leave that more specifics of that for later, but the rate's going up. At x equals 10, something happens. Okay, at x equals 10, the rate changes from positive, so think of this as it's snowing out, but it's getting warmer and warmer, right? It's one of those early winter or late winter storms where it's been cold overnight, it's been snowing, and then in the morning it switches to freezing rain, sort of in that area, and then it starts to rain during the daytime. So the snow that's on the ground at first gets deeper, and then it switches over to rain and the snow starts to melt. So the depth of snow will increase until 10, x equals 10, but then it's going to start to decrease because the rate is negative. Okay, so what you have to connect this to is that if the rate is negative, the original will slope down. If the rate is positive, the rate will slope up. So positive rate, positive slope on original. Negative rate, negative slope on original. Okay, makes sense. So there's something here right now that in terms of things to fill in, that I can fill in very easily. Okay, I can fill this in very easily. And what is that? Well, I now know that x equals 10 will have to be the location of the maximum on the original. Okay, it has to be because that's where it switches from snowing to raining. Okay, it switches from accumulating snow to melting snow. So obviously, if it switches from snow getting deeper to snow melting, the deepest part of the snow has to be the deepest at that location, the x-intercept of the rate curve. So I know right away that this right here is x equals 10. That's where the maximum is. Okay, and with this question, really there's no specific sequence. You're trying to fill in as much information as you can. Okay, so we go back to our relationships. So let's look at this. Well, actually, we should try and fill in anything that's given on the graph. So here's our f at x graph. So I know that f at 2 is given, and f at 2 is 20. Okay, I can go up and across, right? But also, f at 13 is given, and f at 13 is also 20. So here, what do I know then? So I know that the net area of this is the area portion, right? Whoops. This is the area is equal to the change in y value. So the net area has to be 0. Okay, the net area is 0 because why is the net area 0? Well, because there's no change in y value. Okay, there's no change in y value. Let's see if that helps us know something about this. So I'm told that area 1 is 12, okay, positive 12. In other words, 12 centimeters of snow fell. Then I'd have to figure out, well, how many centimeters of snow had to melt? If 12 centimeters of snow fell, and the depth of snow didn't change overall, there's net 0 change, right? Because it went up and then it went down. So if this area is 12, what has to be this area if the net change is 0? Well, I think it's got to be negative 12, right? It's negative 12, so I can put either location. It's negative 12, okay? We know that 12 centimeters of snow fell on the ground, 12 centimeters of snow had to fall on the ground. Last thing, what's the maximum y value? Well, what do I know about the area from 2 to 10? I know it's 12. And the area under the curve, or the area under the rate graph, is equal to the change in y value on the original. So that's 20. So it's 20, and then the area over here between 2 and 10 was 12. So this is 20 plus 12, it's 32 centimeters. Okay, 32 centimeters. And then we notice that it falls again by 12, right? Because it goes up by 12 for the positive area, and then it goes down by 12 for the negative area. And we end up where we started at 20 centimeters of snow. Okay, that's a really, there's a whole bunch going on in that question, but what you will learn from doing these is astronomical. It teaches you so much about relationships between rate graphs and original functions, and it helps you with both branches of calculus that we will study. Differential, which is about slope, and integrals, which is about area. Okay, so pause, rewind, then go back and immediately do this question on your own, okay? Making sure that you understand it bit by bit.